Hello boys and girls, so in this video we are going to continue with our subtopic 8.5 diffractions by a single slit. Diffractions. What is meant by diffractions? So diffraction actually is referred to the bending of light wave as they travel through obstacle or passes through a narrow slit. Okay, when the wavelength passes through a narrow slit, they will be spread out. So the spreading of light, of the bending of light wave, we call it as diffractions. So in order to observe diffractions, obviously we have to make sure that the slit size is small relative to the wavelength of light. So our width of the slit must be small compared to the wavelength of the light. Number 2, the screen is far away. Number 3, the rays are parallel. So normally the amount of bendings depends on the relative size of the wavelength of light to the size of the slit. If the slit is much larger, for example this one, if our slit is much larger than the light wavelength, we will find out that the bending will almost unnoticeable. Okay, tak obvious untuk kita. However, if the slit are less than wavelength, the width of the slit is more, look at this one, then you will find out that the amount of bending is considerable and easily seen by our naked eye. So this is what we call diffractions. So what actually happened when light pass through a single slit? How we obtain the diffractions pattern? So if we refer to figure A, we consider monochromatic light of wavelength lambda passing through a narrow slit of width A. The width of the slit is A, and after that they shine on a distant screen. They shine on the distant screen. What actually happened? So, let us have a greatly magnified view of the slit. Let me magnify the single slit. So, according to the Huygens principle, each point on the wavefront that reach at the slit will act as secondary sources emitting new wavelets. These new wavelets will radiate towards the screen. So, wavelets from one portion of the slit, they will interfere with the wavelet from another portions and generate diffraction pattern on screen. So class, for the theta equal to 0 degree, we find out that the wavelet going straight forward all travel the same distance to the screen. Thus, they will arrive in phase and interfere constructively, produces a bright central fringe on the screen directly opposite to the slit. Anyhow, we might also treat each point on the wavefront is paired with another point at a distance half of the width away. These wavelets all will meet on the screen at a certain angle theta. The path difference between ray 1 and ray 2, ray 3 and ray 4, or ray 5 with ray 6 is the width of the slit over 2 psi theta. If this path difference is exactly half of a wavelength or equivalent to the phase difference of 180 degrees, then we will find out that the two wavelets will cancel each other and disruptive interference results. So, as a result, a dark fringe will be seen on the screen. So, we will observe a dark fringe on the screen. So, this is the diffraction pattern we obtain from a single slit, whereby we will have a white central bright fringe, follow with the narrower alternating dark and bright fringes. All these dark and bright fringes will have decreasing in density away from the center. So at the center, we have a central bright fringe. On either side of the central bright fringe, we might have our first minima equivalent to a first dark fringe, sama dengan first dark fringe, follow with second minima and third minima, and so forth. So between each pair of these dark fringe, there is a bright fringe due to constructive interference. Anyhow, the brightness of the fringe is related to the light intensity. We will find out that most of the light intensity is concentrated in the broad central bright fringe. The higher order bright fringes are much less intense compared to the central fringe, as graph indicates, okay, from this graph, light intensity. So this is the single slit diffraction pattern that we might obtain. So if we refer to the figure given, at the middle, we have the central maximum right in front, right opposite to our single slit. Then follow with the first minimum. Then we have the first maxima, follow with the second minimum, and then second maxima, and so forth. So this is the midpoint of our central maximum. A dark fringe, or we call as minima, will be obtained at a particular angle or a angle theta n on either side of midpoint. Okay, our first dark fringe, first minima, will obtain at either side of our central midpoint, central maximum midpoint, whereby A sine theta is equal to n lambda. A is referred to the width of the single slit. Theta n is the angle for the n dark fringe measured from the midpoint on the screen. Lambda is the wavelength of the monochromatic light we use, and n is referred to the order number. The order number is count starting from 1, 2, and 3. We have plus minus. Why we have plus minus? Because our first minimum, our second minimum, and so forth, it can form on either side of the central maximum. That's why we have plus minus. So, for example, this one will be n equal to 1. Here also is first minimum on another side. So we label it as n equal to -1. Then we have the second minimum, n equal to 2. Second minimum can also form on another side of the central maximum. So this one we denote by n equal to -2. Okay, central maximum for sure will take n equal to 0. Then we might also determine the distance of the n order dark fringe or minima to the midpoint of the central bright fringe. We call it as yn. How to determine yn? Yn is given by n lambda d over a. Same goes for the bright fringe. We can determine the distance of the n bright fringe. I can calculate the distance of the n bright fringe to the midpoint of the central bright fringe is given by yn equal to n plus half lambda d over a. So d, the capital D represent the distance between the single slit and the screen. A represent the width of the single slit. Wavelength is the lambda is the wavelength, lambda is the wavelength of the light we use. N is referred to the order number, plus minus 1, plus minus 2, plus minus 3, and so forth. Then class, we might calculate the width of the central bright. We might calculate the width of this central bright. How we calculate the width of this central bright? So, we can see obviously after the central bright, we are going to have our first minimum on both sides of the central bright. So, the width of the central bright will go from the first minimum on one side to the first minimum on the other side. Okay, I repeat, the width of the maximums, the width of the central bright will go from the first minimum on one side to the first minimum on the other side. So, the width of the central bright is equal to 2y1. y1 is the distance of the first minimum from the central line, from the center point, okay, central line here. So, we are going to have the width of the central bright will be 2 lambda d over A. So, from this equation, we can see obviously the width of the central bright is inversely proportional to the width of the slit. Okay, so the width of the central bright is inversely proportional to the width of the slit. Okay, this is the width of the slit. So, the narrower the slit, when our A is small, we will find out that the more the wave will spread out, whereby the width will become greater. Okay, let us see one animation on this one. So class, refer to the equation of the width of the central bright. We have W equal to 2y1 equal to 2 lambda d over A. So we find out that the width of the central bright is inversely proportional to the width of the single slit. This is the width of the single slit, A. Okay, we represent by A. So we will find out that as our width of the slit increase, the width of the central bright will become smaller. Okay, let us see. So, you observe as teacher increase the width of the single slit, observe what happened to the diffraction pattern. So, this is our width of the central bright. This is our central bright. This is our central bright. So, boys and girls, this is our central bright, whereby this is the width of our central bright. Okay, so observe what happened to the width of the central bright when we increase the width of the single slit. Observe carefully. So as teacher increase the aperture, the single slit, width of the single slit, observe what happened to the width of the central bright. See, as teacher increase the A, you will find out that our width of the central bright become narrower. It becomes smaller. Okay, it becomes smaller. So, we have this conclusion. As the A increase, we find out that the light will spread out less. So the width of the central bright becomes narrower. Dia jadi lebih kecil, dia jadi lebih sempit compare dengan yang asal. See, Yang asal macam ni. Now it become this one. See? Now this is our central wave. Yeah, after we change, we increase. After we increase the width of the single slit, you find out that the width of the central maximum, central bright, will become smaller. It will become narrower. Okay, it become narrower. Alright, so you can see obviously the relation or the effect when we change the width of the single slit. So this is the effect when we change the width of the single slit. Alright. Then class, if we refer to the equation given, the width of the central bright is directly proportional to the wavelength of the light that shine on the single slit. Is directly proportional. It means that as our wavelength increase, we will find out that the width of the central bright will also increase. So you might observe it clearly through these three wavelengths, different wavelengths. For example, purple color, purple light, we have 455 nanometer, and this is the width of the central bright. Then this one is green light, 577 nanometer, which have a longer wavelength. We find out that as the wavelength increase from 455 to 577, the width of the central bright also increase. Same goes for when we increase the wavelength from 577 nanometer to 780 nanometer, whereby is corresponding to a red light, we find out that our width of the central bright will getting more broader. It become broader. Okay, so it become broader. So makin tambah wavelength kita, cahaya yang kita gunakan, central bright kita jadi makin lebar. Dia jadi makin lebar. Okay, so this is the effect of changing the wavelength to the pattern, diffraction pattern we obtain. So the diffraction pattern that we obtain, we can refer to the width of the central bright. Now we continue to one example. We see how we are going to apply the equation that we discussed just now. So we refer to example 5. Light of wavelength 580 nanometer is incident on a slit of width 0.003 millimeter. The observing screen is 2 meters from the slit. Find A, the position of first dark fringe. So I have light of wavelength 580 nanometer. It was incident on a single slit. I incident on a single slit of width 0.003 millimeter. So this is our A. So an observing screen is 2 meters from the slit. So I place an observing screen. How far from the single slit? 2 meters. So the 2 meters will represent by capital D. So we want to find the position whereby we can obtain the first dark fringe. So write down the information given. So wavelength is 580 times 10 negative 9 meter because nanometer. A is 0.003 millimeter, change it to meter, times 10 negative 3 meter. The distance from the screen is 1.6 meters. So I want to find the distance. The position means the distance. The distance of the first dark fringe. So let's say our dark fringe is formed here. Okay, class, for example, our first dark fringe is formed here. So distance means how far our first dark fringe from the center line, the center point of our diffraction pattern. So that one is referred to Y1. So how we find Y1? We can take the equation for the dark fringe minima, n lambda d over A So I put in the value, the n will be 1 because I want to find the position of first start fringe, first. So the n is 1. Put in the value of lambda, the value of d, and also the a, then you calculate, you will get the distance or the position of the first start fringe from the center will be 0.3867 meter. Then we move on. B, calculate the width of the central bright fringe. So width of the central bright fringe refer to W. So width of the central bright fringe is 2 times of the distance of the first start fringe from the center, or we have 2 lambda d over a. So we substitute the value, we will get the width of the central bright is 0.773 meter. C, calculate the angle of the third minima to be observed. So we want to find the angle for our third minima. So since we want to find angle, so we use the equations that we have sin theta. So a sin theta is equal to n lambda. So sin theta for the third minima will be n equal to 3. Substitute n equal to 3. Okay, so put in the others value for lambda and also a, then we will get the angle for the third minima will be 35.45 degree. So this is the concept we have for diffractions of single slit. Then you might try your tutorial question that related to learning outcome 8.5. Now I shall see you on the next video on subtopic 8.6.